Okay, my name's Joe Beeton. I'm a senior security researcher at Contrast Security. We provide security tooling for developers. We have a booth in the corner if after this anyone's interested in more about the kind of products we supply. So let's get started. Cool. So the main part of this talk is about the Java instrumentation API. When I say Java, or JVM, this could be a Java or Kotlin or Scala application. Anything that runs on a JVM can use the instrumentation API. So it was added in 1.5, so that was 12 years ago now. Yeah, give or take. And then updated in 1.6, but it was mostly there in 1.5. It allows you to instrument a running JVM, a Java process, either statically or as in you add a -Java agent to a path, and then it runs that as part of the application, or even dynamically you can attach a Java agent to a running Java process after it's started up. And I'll go through both of those in a second. So you probably use this if you're a Java developer already. If you ever use any sort of test coverage tooling, then you do use the instrumentation API. That's how, in say JUnit, it will, that's linked to a IDE like IntelliJ, and you get a percentage of code coverage. That's done via the instrumentation API, or if you're using JCOCO as part of your build process or any other tool like that, again, it will use this under the hood. In fact, most of those kind of testing tools use JCOCO under the hood, even if they use something on top of that. And also Contrast Assess and Protect product also use this for Java based applications. I'll go into that a bit more in a little while. So how do you do it? So the first part, I'll go to the more interesting bit, which is dynamically attaching. So if you have an existing Java process and you want to attach an agent to do something, it's code-wise, it's actually very simple. That's it on the, that's the entire code to attach a Java agent. Specify a process ID, 1, 2, 3, 4, location of a Java agent, jar, and attach, then detach. And that's it. So hope you all enjoyed this. It really is simple. Well, it looks simple, but under the hood, it gets a bit weird. And so that's what you have on the caller process for what then gets called in the target JVM, the one you're attaching to, is when you do attach, it loads that jar file and calls an agent main method. And then you have code in there that does stuff. And it passes also in the list of arguments that you passed in as part from the attacher process, and an instrumentation class, which gives you lots of information about the running process. And so this is all to be clear, this is occurring within the target JVM. So at this point, it's all within the process you've attached to. And that instrumentation contains a list of all classes that have been loaded, other information about heap space usage and stuff like that, and other things like it allows you to modify the bytecode of existing loaded classes. So how does that attaching process work? So you have an attacher JVM and then the target JVM. So the attacher creates, so you have to pass into the attacher the process ID as we saw earlier, 1, 2, 3, 4. So this process is slightly different on Windows and Linux, and also it's JVM specific. So this is how it works for OpenJDK and Oracle on Linux. This isn't necessarily the same thing that happens on Windows and IBM, Java, or any other kind of odd JVM. It may be different. This is how Oracle does it. So the attacher JVM creates under temp a .attach PID, then presses ID of the file. It then sends a sigquit to the target JVM. This is in Unix. This is an optional. This is a call to quit for that process to kill itself, but it's optional. The process doesn't actually have to adhere to it, and in this case, it doesn't. but this is the signal that they've decided to use. So the target JVM takes that SIG-quit signal, checks for a .attach PID, its own process ID, to see if that exists. If it does exist, it then realizes that rather than someone is trying to shut down this process, it wants an agent to attach to it. It then creates a handler thread, which then deals with this attaching. It then creates a .java PID file, then the process ID 1234. This isn't a file, this is a Unix socket, and this is what's used for inter-process communication between the attacher and the target JVM. So once that file is created, the attached JVM is looking for that file to be that pipe to be created. Once it's done, it attaches to it, and then it sends a load agent, location of the agent jar file, and then to the target JVM. The target JVM gets that location of the jar file on disk, loads it, reads the manifest file, looks for an entry which will give the location of the agent main method. And then calls that method with the arguments and instrumentation class. And from there, it then does whatever code was in that agent. So in the manifest file, it's a bit different to a regular manifest file. You have a few extra things. Pre-main is for when you're attaching statically, so with a dash agent on startup, and agent class is for dynamic. You then have some, in the manifest file, you have some permissions that can be set. Redefine and retransform classes are for modifying bytecode. So it allows the agent to modify whatever code you're running, swap it out for something else, and then your target JVM will use that. And native prefix is for if you want to modify instrument native classes or native methods, because they don't have a native method, if you remember, if you know about Java, has no, is empty. It's essentially like an interface, which then calls the C code. But having a prefix allows you to, or changing that prefix allows you to put in a kind of a proxy method in front of that to instrument it, which you can't do if there's no Java code, because you can't add Java code to a native method directly. Didn't explain that very well, but generally speaking, you won't need that anyway. So I'll give you a quick demo of that. Hopefully it'll work. To give you some background, JBOM is a tool we created. It's open source, to create a bill of materials for a running Java application. This was created kind of after the kind of Log4J, Log4Shell event that happened about Christmas last year, where finding Log4J isn't necessarily easy in an application, because it may not necessarily be a direct dependency. It could be a transitive dependency of something else. You don't necessarily know it's in your application. And so this gives you a way of creating a bill of materials of all of the dependencies in your application at runtime. There are other tools that do similar stuff, but this is different in that you can use it to attach to a running application. So if you did a similar thing looking at your source code, it would be, and you use some of the various tooling out there, it will give you a bill of materials of that jar file, or WAR file or EA file, which you will then load onto a application server. And the application server has its own set of dependencies, which will be on your class path at runtime, but it's not necessarily there at build time. Or you may have plugins that are loaded dynamically at runtime as well. And so this gives you a way of looking at what you really have at the application at runtime rather than just build time, because those don't necessarily match up all the time. So let's take a look. Hopefully I can get this to work. So, okay, so first of all, I'll be using a Spring Boot application for most of this. Well, you might be able to see it, I can't. This is just a regular Spring Boot application. I'll just start it up. That's running. So, first of all, I've got to find the process ID. And then, actually no. So JBOM allows you to, first of all, it will give you a list of all the Java processes running on this machine, my laptop. And so we want this one, which is my Spring Boot application. We will then pass in so now that's started up. I'll attach a debugger to it so we can see what it's doing. So we've attached. And nothing's happened. That's probably the problem with doing live demos. Okay, so I can't work out why that's not working, and I can't really see it. Let's just attach, but it's not. Okay. So I'll just have to explain the code. So what would have happened if I was able to get the debugger working is I can't see a thing. So what would have, so if I go back to the terminal, okay, so, okay, just realised what's happened. There we go. So now we've actually attached to the right Java process. What this will now be doing, so this is attached to the, so at the moment we're attached to the JBOM Java application, not the Spring Boot application. And this will go through, and if I hit play, we'll go to the attach, and as you can see, we'll be attaching to the process ID. We'll load the agent jar, then detach. This will inject the JBOM application code into the Spring Boot application, and then it will run. So what I need to do is attach to both, because previously I attached to the Spring Boot application. That's why it didn't work. So I hit play, and now we've jumped to the Spring Boot application. So what's happened is it's gone through the process that I talked about a minute ago. We would have created a temp file, a pipe, sent the jar file to the Spring Boot application, and now it's called the agent main method within the jar file that's just been loaded. And then if I hit play again, loading into a JSON file, and now what it's going to do is list through all the classes, which I won't go through all. Find the jar file that class file came from, work out its Maven dependency from what the details of that jar file, and use that to build a list of dependencies for the application. So if I just hit play again, go to that. And in fact, I can just attach it. So as we can see, it's gone through, hopefully. We've created a file. And we can take a look at that file, which will contain all the details of all of the dependencies. As we can see, I'll scroll down a bit. You should be able to see, so Jackson data bind, well, Jackson core, and lots of other stuff. That I'm sure you can just take my word for it that there's lots of other dependencies in there. Okay, so that's a dynamic attach. And that's JBOM, which is a tool you can. It's open source. You can. There'll be a link to it at the end if you want. If you're interested in looking at it. So this is very useful if you, if at runtime your dependencies aren't the same as build time, or if you have an application that you don't have the source code for. Like it's a third-party system that your business relies upon, but you don't have the source code for. Let's say Jira or Confluence, things like that. They won't give you the source code, but you want to see if you have Log4J within that web application, which will give you the ability to do that. So that was dynamic attaching. Static attaching is a lot easier. You just add a Java agent flag to the startup with the location of the jar file, and you can add variables to that as well. And on startup, it will call a pre-main method, which is pretty much the same as agent main. It's just different so that if there's any differences required within the agent, it knows which way around it's being called from. And again, that's the location of the pre-main method is in the manifest file. And so very, very simple for static attaching, although it is the one a lot of time is most used rather than attaching to something after it's started up. So the other part of this talk is how those are used, especially in contrast. So we have a tool called Protect, which is a RASP, Runtime Application Self-Protection. There are others, although of course ours is the best. And it works by modifying the underlying application. And it adds instrumentation to the application you've attached it to. And that instrumentation allows us to look at, you have a source and a sink, where a source could be like a Spring Boot controller, where you have a get mapping, and that would be a source. It's data coming into your application. And a sink is a potentially security vulnerable end. What's the best way of describing it? It's kind of a end to your application, which is may potentially has a security vulnerability, like a database, or executing other code, or a command on your operating system, or reading a file, that kind of thing. So you have the source and the sink, and because we're able to instrument your application, we can see where the data was coming in and going out to. We can work out whether there's a potential vulnerability there, and with Protect, if we're certain that there is, we can block that execution. So if it was, say, a SQL injection, and we can work out based on the input, which would normally be just get a username from the database, but it's username and then a SQL injection pattern, and that then goes into the database in a way that's not secure. We can block that at runtime. So it will block a SQL injection, or path traversal, remote code execution, JNDI, lots of other things. Unfortunately, I can't show you that code. But I've created a simple RASP for this demonstration, which will block Log4Shell, which if you're a Java developer, I'm sure you know about, because I'm sure someone asked you whether it was in your code base earlier on this year. And the Log4Shell vulnerability allowed you to, if there was any user data that was being logged, say from a web application, if they were able to add a string like the one below of $parentheses JNDI RMI something something, it would then lead to remote code execution on that server. And you had lots of, I think one of the funniest was Minecraft servers being popped by people just putting into the into the chat essentially this string. But no, you're not, are you? Hopefully you like my terminal, though. Okay, sorry about that. Okay, so where were we? We were there, weren't we? Great. So I'll go quickly. Static attaching. So this is the pre-main method. As I was mentioning earlier, you have, it's very simple. You have a Java agent location, and on startup, this method gets called by the JVM, and that method is in a class specified by the manifest file. Very similar to dynamic attaching, but without all of the weird stuff you have to do to attach to a already running process. RASPs, you all heard me. So again, so this is the string at the bottom. That's a payload for Log4Shell, and that things like Minecraft servers. You put a chat message with that in there, you could get a remote code execution on that Minecraft server. Not just Minecraft servers, any Java application that used Log4J was potentially vulnerable to this. That was using Log4J of a vulnerable version. So you have this payload, but how does that, logging that to a log file, how does that then lead to someone taking over that web application? So Log4J had a, well, it still does, but it's removed most of the vulnerable stuff, has a feature called interpolation. This allowed you to, when you log a message, if you had $parentheses something, it would potentially look that up and output that to the log rather than the string that was there in the first place. So if you had that logger info and username, it would look up in the environment variables, the user variable, and output that to the log instead. And that's not so bad, but it also allowed you to do JNDI lookups. Never really sure why, but it did. And that's where the problem occurred. So in here, so if a user is able to inject a value into the log message, which isn't that hard because a lot of time you'll be logging out, say, the username that's attempted a login, for example. And so if they put in this as the username, that will then be logged. But there's lots of other fields it could be, depending on how that application is set up. So how does that work? How does JNDI work? So yeah, if you sent that logger info to that, you would potentially get a command executed on the operating system. So JNDI, for those that aren't familiar, it's a way of storing data in a directory that can be looked up from your Java, from your JVM, and that could be local, as in the top level, which is getting the JDBC data source and then running a SQL query on it, or it could be remote, and there's a few different protocols that are supported. So here you have an LDAP request, which is then converted into an LDAP object, going to ldap.example.com. So that's all fine. As long as it's a static variable you're passing in to JNDI, you don't have a problem. It's only really an issue when you have the ability, a user or attacker is able to specify what that string will be. Under normal circumstances, that isn't the case, but Log4J allowed that to occur. So if a malicious, if an attacker was able to influence what was in that JNDI string, what could happen? And how does that cause vulnerability. So this is for pre-Java 191, which was from October 2018. After that, there is another way of doing it, but it's a bit more convoluted. So what happens when a malicious JNDI request occurs? So initial context lookup. So it's doing the lookup for the JNDI request to evil server. Obviously, this must be influenced by an attacker. For that to be there. So it makes the request. And the evil JNDI server. So for this to occur, you also need to be able to control the JNDI server at the other end. But if you can specify the host name of the lookup, that doesn't matter because you can set up a JNDI server anywhere, and that server should then, the application will be able to access it, and it will pass out the payload. So this JNDI server passes back a implementation of the JavaX naming reference, and that'll be the payload. So what the application then does with that is it looks up the factory location. So, and if there is a class file factory location, it will then pre-Java 191. It will then load that location using the URL class file loader and load that class into your JVM and then execute it. And that's it really. It's very simple. It allows the attacker can specify what that is, and in that payload you'll execute something malicious usually. So it will load up that location, then makes a HTTP request to the JNDI server. Well, I suppose that's now a HTTP server. That then gets loaded. And this is a potential payload class that gets loaded. So that bytecode is returned. URL class loader loads it into your JVM, and at that point it will then instantiate that, and so it will run the default constructor, as you can see here, and in this case pop a calculator. Although probably something worse than that. In post, so Oracle decided that this wasn't a good idea, that you could, if you can control the JNDI location, it then becomes very easy to take control of the server using this method. And so that's in this update, that was disabled by default. You can still enable remote class loading, but it's a flag you would have to specify. So it's very rare. After 180, there are other ways of doing it. So rather than specify a class file location, if there's a class file that exists on your class path, that can still be loaded because it's not remote. So when the payload reference class is returned, instead of having a payload location, which won't be read, you pass in a factory name. And as long as there is a factory that can be influenced to do something malicious on the class path, that again can lead to remote code execution. One of the more popular ones, which is in Spring Boot /Tomcat, is the Apache Bean factory. And then that can be used to then call the expression language processor, which will then execute a command. And that works up to Java 15 when the underlying Nashorn JavaScript engine was removed. So back to Log4J. This is the JNDI lookup class. This is the class that causes all the problems. So it would be nice if we could change that to say this, and then all our problems would go away. So now let's do another demo, because the first one works so well. Oh, that's gone black. Okay. Good. Go Good, it's mirroring. That's better. So I have a malicious JNDI server running locally. A link to this will be available at the end if anyone wants to run all this themselves. So I have it running on localhost, and I can use this to, if I'm able to inject a JNDI lookup into the application, it will then call this on localhost, but it could be remote, and this will return a payload which will open up the calculator, hopefully. So, first of all, to show that it all works correctly, serialization demo. Cool. So I have a controller here. So I'll just run that. So we have env user, me, and it's not worked. Okay. And if I put in a payload, I really hope this works. So call that. And so that's the Log4J vulnerability. It's opened up a calculator because it's essentially gone through that entire process I just described. Called the JNDI server, that returned the location of a class file that was then loaded and then executed, which caused this to run. So that all works. So if I kill this, and then restart it with a RASP. And of course there is some sort of problem, isn't there? Ah, thank you. Okay, now if I go to my okay, so I'm starting up my Spring Boot application, and I've specified in there a let me just show you that I've I've got a Java agent flag with the RASP and debug as well. So we'll wait till it starts up. So it's now the JVM has called the premain method, which we'll call this. And so what we've had in the instrumentation, you have the ability to add class file transformer implementations, which is what I've done here. And that class file transformer allows you to modify class files. So we've added that. So hit the breakpoint again. So it's going to go through and as it's starting up, every time a class file is loaded in the JVM, it will pass it into this method, and I'm able to modify that so you'll get the byte pull back a bit. So this contains the byte code of that class file, and what we can do is modify that if we wish to. So first of all, it's going to pass every class, so let's just get to that breakpoint, otherwise it will take forever. Okay, so now we have the JNDI lookup class that we want to modify. Now that we have it, we're going to load this up into ASM, which is a bytecode manipulation library. It's not the only one. It's fairly low level. There are more easy ones to use if you're new to this kind of thing. ByteBuddy is probably the best one, although that is built on top of ASM, because ASM is quite low level. Everything kind of built on top of it. So I'm going to load this into ASM, and then once that's done, it will call every method in that class, constructor, the lookup method that we're looking for, and anything else. And this method adapter will be called at the beginning and the end. We're only extending the end method, and from there we can make changes. So, looking for the okay. So now into the lookup method. First of all, just to show you what the instructions look like. This is the original JNDI lookup method. It's quite large. These are all opcodes and stuff. I'm not going to try and work out what those mean. But as you could see from the screenshot earlier on, it's a reasonable size method. So what we're going to do now is clear that set of instructions, because we don't want any of that. Then add just 2 instructions of our own. A const null, a null object, and then return to return it. So we're just adding those 2 instructions, inserting that list into the instruction list, and then returning it. And that's it. So that's done. So we're not just, so that will then now be returned to the class loader, and the class loader will load our modified version rather than the original version. We're also writing it out to disk to make it easier to see. So I can show you that in decompiler in a second. So that's now run, and the application has started up. So if we take a look at our demo application where it was written out to, JNDI lookup, this was the class. This is the decompile version, and the lookup method is now being, all of the logic's been removed, and we're just returning null. So hopefully we've we've patched the Log4J vulnerability. Well, let's find out, because we just hit this again, and nothing. It's not interpolated that into a result. It's just given you the plain text of it, and no calculators popped up. So that's hopefully worked. You can also do this dynamically. You can do the same thing using the dynamic attach as well as static attach, and the end result is the same. But so yeah, what we've done is looked up the JNDI lookup method, removed its contents, returned null, and therefore blocked the vulnerability. So using this method and similar techniques, we're able to block other more serious issues. This same RASP I've created also blocks certain deserialization attacks in Java. It's available. There'll be a link at the end if you want to take a look at it. It's not for use in production. It really is just a demo to give people an idea of how it works. Really don't use it. It's not good. And that's about it. So here's the, just realized it wasn't on. There we go. Okay, so this is the list of links. This is all of the code I've run today. You can take a look at all of that. There's also, we have, Control Security has lots of developer resources and different scanning tools that you can use as part of your pipeline or run locally. And I'm sure there'll be someone at our booth who will give you a better demo than I can do.